Welcome, ladies and gentlemen, to some Integrated 2 Math. In today's episode, we will be discussing Chapter 6.1.4, which is Radicals and Fractional Exponents. I want to begin with an example here, which is pretty easy. If I was to ask you for the square root of 4, I don't know if anybody would have any trouble with that. In fact, if I told you that your entire grade relied on your ability to simplify the square root of 4, I think everyone would get 100%. And that's because the square root of 4 is simply 2. Now from here, the point of this problem is not to understand that the square root of 4 is 2. It's to get this intermittent step, and if you notice, I left quite a bit of space in between the equal signs here. And so what I want you to be able to start seeing is that the square root of 4, if I wanted to actually rewrite him as an expression that had an exponent in it, what I would say is I would call him 4 to the 1/2 power. And this really is the point of the lesson, learning how to convert between exponential and radical looking forms. So the first couple of examples we're going to do is we're going to just give a few radical exponents, radical expressions, and I'm going to have you convert them into exponential expressions. So give me a second and I will get those examples up. And we are back with some examples here. And so again, before I even find out the answers to these, what I'm going to do is I'm going to go ahead and convert them into radical form. So remember, 9 to the 1/2, right? I'm going to go and convert that into radical form. So what I'm going to do is I'm going to actually use this in reverse. So this is saying the square root of 9. And then similarly, 8 to the 1/3 this time, instead of 8 to the 1/2, it'll be 8 to the 1/3. Instead of saying the square root of 8, right? Because this would normally be called the square root of 8 because something squared would get you that value. Since the square root of 9 is 9 to the 1/2, I'm going to say the third root of 8, or the cube root of 8, would be equal to 8 to the 1/3. And then same thing here. Likewise, it would be the cube root of 64. And this would be the square root of 27. Now notice how under each square root, I'm not putting the 2 right there because the square is implied. That 2 is implied when you have nothing there. But any higher powered roots, you definitely want to put that number next to the rad sign. That way we know which root you're taking. So what do all these things equal? Well, from here I'm going to go ahead and simplify all of them. And so what I'll do is I'll go ahead and simplify the ones that can be simplified quickly first. So clearly the square root of 9 is 3. The cube root of 8, so the number that multiplies by itself 3 times to get 8 is going to be 2. And then the number that multiplies by itself 3 times to get 64 is going to be 4. All right, and if you are wondering, 4 times 4 times 4 does in fact equal 64. Now from here, the square root of 27, well, we can't really find that out quickly, so what we're going to do is we're going to do the return of an old friend. So that's 9 and 3 underneath square roots. That guy becomes a 3, so this becomes 3 rad 3. Now, another way of looking at him, if you wanted to, now I would be happy if you left the answer in this form. Another way of looking at this, though, would be 3 times 3 to the square root. Well, we saw in the last diagram up there, square root is like to the 1/2 power. And if you wanted to, you could leave them like this. I will show you a way in just a second on how to simplify an expression that looks like this, except you guys probably already know how to do it. So let me go ahead and throw some more examples up, and I will join you in a second. With these 4 examples, what I want you to pay attention to right now is the idea that each of these fractional exponents has one thing in common. And that is that all of their numerators are 1. The way they're going to work this problem to make it harder is they are going to give you fractional exponents that do not have a numerator of 1. So how do we deal with that? If I gave you something like 27 to say the 4/3 power, what you want to do is you want to identify what each piece is doing. And I'm going to tell you what each piece is doing. Well, the numerator of the fractional exponent, this is what we call the power of the base. So 27 is effectively being raised to the 4th power. So in this example, I've been writing it down, 27 to the 4th power. Okay. The bottom number is the root of the problem. That's like saying 27 to the, looks like 1/3 power. Or it could be the cube root of 27. So when you combine these two ideas together, what you get, effectively, is the cube root of 27 raised to the 4th power. Because the 3 will apply as the root, the 4 will apply as the power. So, how do we simplify this expression? Well, I will tell you now, 97% of the problems require the same move. And what it is you do this. You root the base down first, and then you power the new base up. Like I said, 97% of the problems, and in fact, I'll give you an example where that rule doesn't apply. So what we're going to do is I'm going to take 27 and I'm going to apply this 3rd root to it. So what I want is I want the 3rd root of 27. I want this step first. So what number multiplied by itself 3 times gets me 27? Well, that's 3, right? This whole thing becomes 3. But remember, what have I not applied yet? I have not applied my 4th power. So that 3 is still being raised to the 4th power. So what I'm going to do now is I'm going to figure out what 3 to the 4th is. That's 3 times 3 times 3 times 3. Those guys multiply to become 9. Those guys multiply to become 9. 9 times 9 is 81. So again, to recap what I did, I rooted the base down, and then I powered the new base up every single time. That's what I'm going to do, except for in a couple of examples. And you'll see when you don't have to do it. It's pretty obvious. So again, why don't I look at another example like this, like 8 to the 2/3 power. Again, what am I going to do? Now here's the thing, is I could power this thing up if I wanted to. I could do 8 squared and call him 64. And then the 2 would be gone, leaving me 64 to the 1/3 power. And if I knew my cube roots really well, I would know that this thing actually is 4. The reason why rooting the base down is so much more advantageous most of the time is because small numbers in general are easier to manipulate and work with than large numbers. So usually we feel more comfortable with small numbers, so it's easier to root things down first. So let me show you what the same problem would look like if I was to root it down. So 8 to the 2/3, I would apply the 3rd root first. So the 3rd root of 8, in other words, a number that multiplies by itself 3 times to get 8, is 2. But remember, I haven't applied this squared yet, and 2 squared is 4. Either way you cut it, you get the same answer. So let's do a few examples of when you have when you have fractional exponents that are not denominator 1. Let me clean up the board real quick. Alright people, and here we are with the last 4 examples of this lesson. So remember, in most of the cases I'm going to do rooting down first and then powering up second. So I hope you have that in your notes. First thing I'm going to do is I'm going to look at this example here with the 16. I'm going to go ahead and box up the root because I'm going to root him down first. So I always draw this same, it looks like almost like a, almost looks like Utah of sorts. And what I'm going to do is I'm going to go and take the 4th root of 16. Now this is going to be some number sense on your part. You're going to want to know what number multiplied by itself 4 times will get you 16. If you want to pause for a second and try and figure out that number, go ahead. That number is 2. Now, after I've taken the 4th root of the 16 to get 2, this 5 will jump in and become the exponent. And then 2 to the 5th is going to be something. Well, that's actually not that bad, because if 2 to the 4th is 16, multiplying by one more 2, or a 5th 2, would get me 16 times 2, which is 32. So 32 ends up becoming the answer. In the next example here, 216 to the 2/3 power. Again, I'm going to go ahead and root it down. Now again, I could square 216. I could. That'd be a really large number, and I don't want to deal with it. Right? So I think it's easier to work with a smaller number. So taking the cube root of 216, meaning a number that multiplies by itself 3 times to get to 216, that would be 6. And then 6 squared, right? Because I haven't applied the 2 yet. The 2 comes in as the exponent. I end up getting 36. And then, here we go, 25 to the 3 halves. Again, I'm going to go ahead and draw my little Utah-looking state right here. 25, the second root of 25 is like the square root of 25. Well, what times itself 2 times gets me 25? Well, that's 5. And I have not yet applied the 3, so that gets me 125. And I forgot to box that answer. Now, at the beginning of the episode, I talked about 97% of these types of problems require you to root down and then power up. This is the exception right here. The problem with this is that if I attempt to root this guy down, right, and again, I told you you'd be able to tell pretty quickly, and I hope you can. If I attempt to root him down, what is the cube root? What is the square root of 2? It's not anything clean, unlike these last examples, right? The 4th root of 16 got me 2. The 2nd root of 25 got me 5. The 3rd root of 216 got me 6. The 2nd root of 2, that's the square root of 2. It's not clean. This does not help me. This doesn't help me solve the problem in any way. Except it might. If I was to actually power up first, and I can do that, I can power up first, 2 to the 3rd power is 8. But remember, this time I haven't applied the 2nd that's on bottom, so it's really 8 to the 1/2. So I could call him, instead of 8 to the 1/2, I'm back to the conversion now, where I call him the square root of 8. And then I can break him apart and call him the square root of 4 times the square root of 2. This guy will become 2, the rad 2 comes along for the ride, and there you go. So that is the first part of these examples. I'll be back with some more exponential properties. And we are back with some exponential rules with fractional exponents. Now, if you're wondering how these exponential rules that you learned in Integrated 1 apply, they apply in the exact same way, except now we're going to have fractional exponents to deal with. So when we have 2 bases being multiplied together, and the bases are the same, what we do is we add the exponents. So in the past, you would deal with things like this, like x squared times x to the 6th, and you would know that that's x to the 2 plus 6, which is x to the 8th. Well, to extend this idea into fractional exponents, now I'm going to give you an example that looks like this. I'm going to give you x to the 3 halves times x to the 7 thirds. And now from here, that's going to turn into x to the 3 halves plus 7 thirds. And in order to add these two guys together, we need a common denominator. So that will be 6. So in order to turn this thing into a 6, I'm going to go ahead and multiply everything by 3. So that's 9 over 6. I'll multiply the top and bottom by 2, so 14 over 6. Ultimately, what I end up getting is x to that power. So x to the 23 over 6. So again, it's the same rules. You just have to apply a little bit of common denominator work on here. So same thing applies with the division rule. If we are dividing 2 bases, we would subtract the exponents. And so in the past, you guys would have something that looked like this. You would say x to the 2 divided by x to the 6th, and you would get x to the negative 4, but since this exponent was negative, you would know to bring him to the bottom and become 1 over x to the 4th. Similarly, if I was to do something like that for my fractional exponents, I could have x to the 4th minus, or rather divided by, x to the 9/4. And again, I would have to subtract the exponent. So I would get x to the 4 minus 9/4. So common denominator again would be 16 over 4 minus 9/4. So I would get x to the 7/4. And then the last example here, x to the m raised to the n, power raised to a power. What we do is we multiply the exponents together. So in the past, you would have something like x to the 4th squared that would get you x to the 8th. In the example that I'm going to give you with fractional exponents, it would be, say, something like x to the 7/8 raised to the 2nd power, and that would become x to the 14/8, right? Because 7/8, I'll even do it out for you, 7/8 times 2 would get me x to the 14/8, and I can reduce that fraction, and I will. That's going to be x to, they both divide into 2, so 4/7/4. Now, one of the rules that I haven't mentioned yet is when you have x to the negative m, the negative exponent always brings the base to the bottom, and the exponent becomes negative. So the way it applies to fractional exponents would be something like this, where you have x to the negative 1/4, that would turn into 1 over x to the positive 1/4. And again, we haven't learned about rationalizing the denominator yet, so at this point I would expect you to leave him here. So this rule, the negative exponent, can happen at any given moment in the other problems. So for example, going back to the power raised to a power, if I have x to the 2/3 raised to the negative 4th power, that would be x to the, these guys are going to multiply, a positive times a negative is a negative. It'll be negative 8/3, which you would then drop to the bottom and call them 1 over x to the 8/3. And I think that will wrap it up for this lesson. So hopefully it makes sense. If you have any questions, please leave them in the comments section, and we will see you in the next episode.